Hey everyone, I'm Sathya. Today, Mofei and I are going to talk about the internals of the React compiler. You don't necessarily need to understand the compiler to use it, but we think it might be useful to build an intuition of how the compiler works. So React was the first to popularize the declarative approach of writing UI code. At its core, React's all about the idea that your UI is just a reflection of application state. Right? Like, we know that React represents your UI as a tree. The tree is composed of nodes, each of which represents a component. When state or context changes, React needs to recompute the UI. React re-renders the component and all its child components to recompute the new UI. When your component is re-rendered, every single value in your component is recomputed, even if it doesn't depend on the state or context that changed. You could say that React is like too reactive even. So imagine if we could only recompute values or components that did actually change. And what if we could do that automatically? Well, we showed React compiler yesterday, and that's exactly what it does. But how does the compiler actually understand your components? Before I joined the React team, I worked on V8, which is the JavaScript compiler in Chrome. V8 would model the JavaScript specification to understand how to optimize your code. And similar to that, the React compiler uses the rules of React to optimize your code. The rules of React primarily exist to help you build complex UIs without bugs. The compiler being able to use it is just a bonus. The rules of React are probably familiar to most of you, but it's OK if you don't follow these today. For the most part, the compiler will detect if you violate these and skip compiling those components. Let's go over a few to understand what they are. We're all familiar with this rule. Components and hooks must be pure. Strict mode already helps you catch violations of this type of bugs. In this example, the hook isn't idempotent. The return value could change between calls without React knowing about it. Instead, you should use the useSyncExternalStore hook to let React know when the value changes, so React can re-render your component. Now, in this example, the component is reading and writing from a guest variable that was declared outside it. Similar to the previous example, calling the component multiple times will produce different JSX. And what's more, if other components read this guest variable, they will produce different JSX too, depending on when they were rendered. That's simply not predictable behavior. Instead, you can fix this by passing guest as a prop instead. Now your component is pure, as the JSX only depends on the guest prop. Now consider this example, where we modify the item prop directly to add a new URL property. This breaks encapsulation, right? Now, if the parent component sent the same item to some other child component, the child component is going to get the surprise URL property, whether it wanted it or not. Instead, always create a new local variable and modify them. Once values are passed to a hook, you shouldn't modify them. Like props in JSX, values become immutable when passed to a hook. One important principle in React is local reasoning, the ability to understand what a component or hook does by looking at its code in isolation. So hooks should be treated like black boxes when they are called. Like in the previous example, always create a new local variable and modify them. When you use JSX in an expression, React may eagerly evaluate the JSX before the component finishes. This means mutating the values after they're passed to the JSX can lead to outdated UIs, as React won't know to update the component's output. So don't mutate values after they're being passed to JSX. Move the mutation above the JSX, or just create a new value. So those were some of the rules of React. Like I said, the rules exist to help you build complex UIs. We're not adding new constraints just for the compiler. It's for building UIs. But they also help to carve out like a safe space for the compiler to optimize your code. These rules are what makes the React compiler possible. Now we've learned about what information the compiler can use to optimize. But how does the compiler actually work internally? I'd like to invite Mofei on stage to talk about how the compiler works.
Hello? Oh, hey y'all. So Sathya just explained how the rules of React help humans write more maintainable code. The same rules, well, more generally, the way that we write React code is also very useful for tools like React Compiler, ones that analyze and optimize your code. So for the rest of this talk, we're going to talk about some compiler internals. And what's a better way to do that than write one ourselves? So 20 minutes is not a whole lot of time. So just to be clear, we're not writing all of the compiler. The one that we write should be able to handle very basic JavaScript, basically making objects, accessing fields, calling functions, and returning stuff. And it should do one thing, add memoization code so that we don't need to. So if we do this right, at the end of the talk, we'll be able to take components that look like this, ones that we write, run some build and compile command to generate a memoized version. So the compiled result should have used memos, like on the right. And just to clarify, the real compiler does not add use memos, but just for readability. It's much easier to read this. OK, so let's get started with the demo. Click a button. Cool. OK, so this is my coding setup. On the left, I have the compiler, which we need to write, all of it. And on the right, I have a terminal program that will need to run our compiler as we're writing it. It's useful for seeing stuff like console logs. So if I console log here, it's going to show up on the right. As you can see, there's another file here called input.js. And this is the input to our compiler. So whatever I type into this file, that's going to get run on the right. So if I type hello, it shows up. As you can see, we're not transforming anything right now. The output is exactly the same as the input. So I'm going to paste in a tiny React component that will let us test our compiler as we're writing it. It looks really small, but I promise it's more than enough for us to work with. And now we can get to coding. So we're going to use a popular library called Babel to parse our JavaScript input. And the way to use Babel is you pass in functions to this visitor field. And I'm going to write a callback for function declarations. So Babel should call this every time it sees a function in its input. So if I print the function name in here, I should see found music player on the top. OK, so this does get called by the feed function and, sorry, music player function. Our next step is to take the information Babel passes to us and turn it into a representation that's easier for us to work with. So I'm going to call a function called read instructions, give the Babel function to it, and store it in a instruction variable called instructions. And let's just see what this instructions looks like. OK, it's just a collection of instructions. And hang on, I can actually print them out. If we look at the printed logs, the first thing to notice is that each instruction produces a value. So we're printing out a special name for this instruction value, the $0. But in our code, it's just represented as a number, the ID of the instruction. Some types of instructions might have operands. Like, for example, instructions 0 and 1 are parameters, and their operands are string names. If I keep on going, the next instruction is songs, which is a property read off of an object, and its operands are the number 0 as well as the result of instruction 1, the parameter songs. Okay, so also one more thing to notice is that one normal line of code might map to many instructions. So just so we get all of them, this really low-level flat representation makes it really easy for us to trace through how data flows through a component. It also lets us apply memoization at the instruction level, which means that our generated use memos can be pretty granular. All right, so let's get back to writing our compiler. We don't have anything yet. So in order to actually transform our input code, we're going to replace the input code's function body. And I'm going to take the body, and if I pass in an empty array here, we'll see that the output on the right gets no instructions in its body, not what we want. We're going to use a helper function called CodeGen.js to synthesize a new function body for us off of those low-level instructions we just saw. And we are going to use the result to replace the original function body. So our generated output looks pretty exactly the same as the input, except for missing a comment. We don't represent comments in the low-level instructions, so that didn't make it. And now we're finally done with writing all the setup. So far, we've converted our JavaScript input into a very low-level representation here. And we've managed to generate the output from scratch using this representation. And we can finally get to the fun stuff, the part of the demo where we start generating use memos. So we're going to start by defining a function. It's called analyze. It takes in the set of instructions as a parameter and returns a set of values describing those instructions. A set of information describing those instructions. And what should we do inside of analyze? Well, we want use memos, right? Maybe we should just tell CodeGen to memoize something. Well, I don't really know what to do. So as a start, maybe every instruction should be memoized. We need to call it. Analyze. Going to call analyze instructions and pass what analyze returns to CodeGen. So this is how we're consuming the information. And now we see some pretty crazy looking output here, right? Like, hopefully React compiler doesn't actually do this. It's a lot of use memo calls. We're going to talk about that, but before that, I noticed something else really interesting in the output. There's just 2 lines of code in the input we gave our compiler, but it was able to split up all of those into separate use memo calls. So we have 2 lines of input and 10 use memo calls. The reason for this is because of our low-level representation. So we see that every instruction can correlate to a use memo. All right, so let's go back and figure out why we have a billion memo calls. Well, here I print the result that function returns, so maybe you can take a look at those. Okay, so we're memoizing everything. Why do we? That's right. We're memoizing everything. So maybe we can take a look at the instructions and figure out which ones actually need to be memoized. So maybe we don't need to memoize songs at index 0, for example. If I'm reading a property off of an existing object, that's not going to create a new object or a new function. Similarly, reading description shouldn't need that. And we can also walk through this representation. So params, read properties, declarations, load constants. But call, that one. If I'm calling out to another function, that function might create and allocate a new object to return. So call instructions are something that we do want to memorize. So, okay, maybe we should look at the instruction kind to tell us. And call instructions should be memoized because just like we said, it might create a new object to return, but if we also create a new object directly, that should be memoized. And now our output looks a lot more reasonable, right? But it still doesn't look quite right. Oh yeah, we're missing the dependency arrays. Well, what should we do here? How do we fill in those dependency arrays? Well, maybe we can take a look at the low-level representation to give us a hint. So we skip to the call instruction, which is what we're actually memoizing. And I see that the call instruction uses two other instructions. This thing called 5, which is this global variable array that we're reading, as well as the parameters songs1. Okay, so maybe my dependencies are just the results of other instructions that I use. Every value that I use, maybe I should just add that to the dependencies. And pass down dependencies. There we go. How does that look? Any issues? Just a couple of issues, so you might be a little confused which one we're going to talk about. So yeah, it's the dependencies array, and that's what we're talking about. It's not quite right. Why is the global array object in there? I mean, I wouldn't write this code, right? Let's go back and look at what the analysis function returns. Oh, okay, so it returns that we're depending on array. We told Cogent that, instruction 5, which is array, is a dependency, and that's how it made it into the use memo deps array. But array doesn't need to be a dependency. As Sathya just explained, developers writing React code promise to write pure idempotent components, which means that any global values a component uses has to be a constant. So according to the rules of React, array doesn't need to be a dependency. Okay, so maybe we should add something as a dependency only if it might change across renders. So if we had this set of things that might change, we can use it like so. And now let's write a helper function to compute what might change is. Get values that may change, passing it function, and returning may change. And now we actually need to write this. So it's a function called get values that might change that consumes instructions and returns a set of instructions that may change. So how do we know whether an instruction might change across renders? What should go here? Starting to get a bit of deja vu. Maybe this is similar to how we calculated should memo. Maybe the instruction kind should tell us. So Sathya just explained that the only thing that can change across renders are really parameters and what's returned by hooks. We're not going to talk about hooks here because that's a bit more complex, but let's handle the the parameters. So if the instruction kind is a parameter, it might change. And now we see our output looks pretty good. Array is finally missing from this deps list. But now we're missing a couple, right? We have this thing called make songs. And make songs is used in this onShift call. That doesn't make it into the dependency array. What's the issue with that? Well, if we look closer, make song reads from user, which is a parameter. It might change. So as a result, make song might also change across renders. So not only do we have to look at the instruction type, we also have to look at the values that this instruction uses. And if a value that this instruction uses might change, this instruction itself might change. So ID is this instruction that we're currently processing, and used is a value that it uses. And finally, our dependencies array look a little bit more sane, right? But there might be something else in the output that looks a little bit off. Any guesses? So we're done with building dependency arrays. It's not there. Unshift. Huh. What's wrong with that? Well, according to the rules of React, if you call useMemo, or if you memoize a value, you shouldn't change it after the useMemo call. So here we're calling array.from to create a new list of songs. And after the useMemo returns, we're kind of writing to it in another useMemo. So if you're all doing code review, you've all failed except for that guy. This would break prod. You might get some really nasty tearing errors. So the issue is that these two useMemo blocks should actually be merged. Really, these three should be merged into a single one, so that we're kind of creating array.from songs and changing it within the same memo block. So this isn't possible in some languages that you see, like Haskell, where if you're working with record types or primitives, but because this is JavaScript and just plain arrays, this can happen, and we need to take care of that. So the solution is pretty similar to how we figured out how to avoid adding global constants into dependency arrays. So we're going to fix this here. Fix writing to existing objects. So to fix this, I need to first understand which instructions produce values that are writable. So we're going to declare another function, another helper function called getWritable values. And this should return a set of values that might be, writable, like objects, arrays, really any non-primitive, non-frozen types. And what to put here? Starting to get a bit of deja vu again. Maybe we can handle this the same way that we calculated may change. If we look at these set of instructions, really every time I call a function, I have a call instruction or an object instruction. That might give me back a new object, which is writable. I can't write to things like props or what hook calls return. So I'm going to check the instruction kind, and if the instruction kind is a call or an object, that is a writable value. Nothing's changed because we're not writing this. Okay. Also, just like how we calculated may change, anything that you read off of a writable value, like if you're doing array access off of an existing array, that might be writable as well. So we're going to look at the instructions that this one uses, and if it is writable, if it uses a writable value, the result might also be writable. And this is really an over-approximation here. We're really calculating the set of maybe writable values, and this is maybe different from type systems like TypeScript or Flow that calculates precise values. Since React compiler produces memo blocks, it's better to be overly conservative and assume that values are writable than assume that they're not. So this is really an over-approximation of all the values that are writable. So this part is done. Now let's figure out the second part. Now that we've figured out that array.from might produce a writable value, we need to figure out that unshift might be writing to that. How do we do this? So get writable values. And similar to our previous analysis for dependency arrays, we're going to get the writable values first and then use them. So the only instruction that might modify or write to an existing object in our little instruction set is calling out to an extra function. We don't have things like reassignment or assigning. We just have like 5 instructions. So this is pretty simple. If the instruction kind is a call instruction, that call instruction might be writing to things that it consumes. So we're going to look at what values that call instruction uses. And if that thing is writable, we're going to assume that maybe this is a write. So we're going to tell CodeGen this by writing into this results list. This is some cruft for creating a new one if we don't have one yet. And we're going to just add the current instruction. So if I am a call instruction and I'm maybe reading this or arguments that are writable, I might be writing to them. And now our output actually looks good, hopefully. Any code reviewers in the audience with a discerning eye? Okay, everyone's too afraid to say anything after that last mistake. Okay, we're done writing code. This is good. So I know I just said that we're done writing code, but I'm really happy with this compiler we just built, and I just want to try changing my test case. I just want to add one more thing. If I wanted to push my favorite song to the end of all of my music players, that should be fine, right? Oh no, what's the issue there? It's the exact same issue as before, except there's one little difference. Unshift thinks it's reading from array.from, thinks it's changing array.from, and push thinks it's changing this whole other value called items. And we currently don't know that array.from and items might be the same thing. So if we step through, if we print out the set of writes and step them through, we see that on instruction 10, which is declaring items, we think that the only write to items is instruction 12. But that's not the case, right? Items might actually be the same as array.from. That's a bummer. I think we should give up on this thing. No React compiler. It's too hard. Well, fortunately, I know a one-liner that can fix this. It's really quite simple, much easier than everything else we've done. If we can just understand this thing called aliasing, life would be good, right? So now this is the end of the demo, but I want to talk about one more thing. So this use memo is not actually what React compiler produces. So the compiler will generate a different type of output with if branches that's a little bit more performant than use memos. And it also gives you some kind of more opportunities to do branches or conditional memoization. So I'm going to give you a peek of what that looks like by passing in this optional third parameter. It's just full of these called enable real output. So this is what the real output would look like. Cool. Let's see. Okay, I'm glad it worked. I had no other backup slides prepared. My teammates all asked me, what are your backup slides? And I told them we're doing this one. So yeah, we wrote React compiler. That's pretty cool. but you're telling me that it only takes like 20 minutes to write? Well, we wrote kind of two parts of React compiler, the part where we understand memoization, like the dependencies, as well as understanding mutability, instructions that might modify other instructions. There's kind of a lot of other very fundamental parts of the compiler that we haven't touched on. And just to give you an idea, the bolded parts are kind of passes that we've walked through, and the rest is you can find on the playground if you're curious. But I mean, we should still be really proud of ourselves. Analysis that looks pretty much exactly the same as the code that we write powers the React compiler, as well as ESLint rules and a lot of other JavaScript transforms. I mean, in the end, it's all just sets and maps that store information about some representation of your JavaScript. So, thank you.